Hi everybody, we're doing a video today on 2.6 higher order derivatives. Now this is one of these things which sounds much worse than it really is. Second, higher order derivative just means if you take a derivative of a derivative. It means I have a function, I take the derivative, and then I get a new function, and now I take the derivative of that new function, and that's a higher order derivative. So basically, let's just do an example. This is by the how we write it. Y prime is the derivative. Y double prime is the second derivative, or the derivative of the derivative. So let's just jump right in. I don't want to make this more complicated than it really is. So f of x is equal to 2x to the fourth minus 3x squared. So that's f of x. Now when I take the derivative of that, that becomes 4 times 2, which is 8. X to the third, because you know the exponent drops down 1. And this becomes 6x. That's it. So that's the derivative, but now we're calling that the first derivative. Now, if I take the derivative of the derivative of x to the third is 3x squared. The 3 times 8 gives me 24, x squared. And the derivative of 6x is just plain 6. So that's the second derivative. Now, third derivative is to take a derivative another time. So the derivative of x squared is 2x. The 2 times 24 is 48. So I got 48x. The minus 6, that's just derivative of a constant, just disappears. And that's it, 48x. Now I'm going to take the derivative of that. So that'll be the fourth derivative. So the derivative of 48x is just 48. And now I'm going to take the derivative of that. And the derivative of 48 is 0, because I take the derivative of a constant, it gets 0. Now, if I take a 6 derivative, 7 derivative, 8 derivative, it's just going to all be zeros at that point. And that's the way it is with polynomials. When I have a polynomial, if I keep on taking derivatives, eventually I get down to where it's just all zeros. That's not the way with every function in the world, but that's the way it is with polynomials. Let's look at this example right here. Let's actually work this one out. So take my snipping tool. Let's actually do this. All right. So f prime. That's going to be 3 times. That's going to be 18. Let's see, x to the second. Minus 4x, and that's it. Because the derivative of x to the third is 3x squared. Actually, let me put that in as I'm going to actually put that in as a separate step. Just to be clear, I'm going to put that in as a separate step. So this is so the derivative of x to the third is 3x squared, but the 3 times the 6 gives me the 18. All right, I'm not going to go through that explicitly every time. That's the idea. Now, f double prime, that equals, well, so we have 18. So 2 times 18 is 36. And then just plain x. And that's going to be whoops. And that's going to be minus 4. And now the next derivative, x f prime prime prime, and that equals, well, that's just going to equal 36. And now if I go again to f, now I don't write prime 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 prime. I just write it this way. I make a little thing here, and I just write a little 4, because that's the fourth derivative. And that's going to equal 0. And if I do a fifth derivative, that's also going to be 0. And I can keep on going on forever, and they're all going to be 0 at this point. But so because I'm taking a derivative of a derivative of derivative, we call it a higher order derivative. So when I say higher order derivative, it sounds super complicated. But if I just say the derivative of derivative, that's not so. That's all it is. All right. Anyway, let's back to the book. So let's find g triple prime for this function. So it works like this. So the derivative of t to the fourth is 4t to the third because I have the negative there. 2t to the third, so 3 times 2 is 6, and then the 3 drops down to 2. The derivative of t is 1. The derivative of 4 disappears, and that's my second derivative. Now, if I take the derivative of this new function, 3 times 4 is negative 12. The 3 drops down to 2. 2 times 6 is 12. 2 drops down to 1. And the derivative of a constant just disappears. And if I take another derivative, third derivative, so 2 times 12 is 24. Don't forget the negative keeps on coming down. T to the first power, that's plus 12. And now they want us to find g triple prime of 2. So all I got to do is, now that I got down to g triple prime, which is this last guy right here, now I got this last guy right here. I just gotta plug in 2 for t. Oh, 2 for t, t for 2. Yeah, that's t. So g triple prime of 2 is equal to negative 24 times 2 plus 12, which is comes out to negative 36. And that is that. So you're just basically taking a bunch of derivatives and then plugging in a number. So again, when you see the title of this chapter, higher order derivatives, it sounds like super complicated, but it's really no big deal. Now, I told you we've seen so far that when I keep on taking derivatives, eventually I just get down to all zeros. Now that's not always the case. That's always the case with polynomials, but it's not always the case with other functions. And here's an example where it's not going to be the case. That's y equals 1 over x, or x to negative 1 power. So the derivative of this is going to be negative 1 times x to negative 2. The derivative of that, which is negative 1 over x squared. The derivative of this guy is going to be that bring down the negative 1. And here I get negative 2 times x to negative 3, which is 2 over x to the third. And now the next derivative becomes, well, the negative 1, negative 2 keep on coming down. And now I bring down the negative 3, x to negative 4. That's a derivative with the power rule. And now I have negative 6 over x to the fourth. And I do it again, the same thing. I get 24 over x to the fifth. Notice that the sign keeps on alternating, plus minus. And the numbers here, the numerators, I don't know if you recognize it yet, but the numerators are what we call factorials, meaning that's 1, that's 1 times 2, that's 1 times 2 times 3, that's 1 times 2 times 3 times 4. But that makes sense because that's what's happening here. And but the sign keeps on changing, alternating, I should say. Already. I just want to say something on this. I'm not going to do this whole problem here, but it says here, as they give another problem, find the fourth derivative of 1 over x squared. Well, I already have in this problem here negative 1 over x squared. So all I got to do is that's the first derivative is going to be negative 2 over x to the third. The next derivative will be positive 6 over x to the fourth, and then negative 24 of x to the fifth. So the first 3 answers I already have. And now I just have to do one more, and that's going to wind up being negative 120 over x to the sixth. Okay. Now here's something famous which you may or may not know from physics, that S stands for position. Position, distance, we're going to say position. The derivative of position is velocity, because velocity is change of position. Velocity means I'm going from here to there. And the derivative of velocity is acceleration. because acceleration is a change in velocity. I mean, if I'm driving at 20 miles an hour, all of a sudden I speed up to get to 30 miles an hour, so I'm accelerating. Okay, so a ball is thrown upward from the top of a cliff, 160-foot cliff. You see right there, and the initial velocity of the ball is 48 feet per second. Means the person throws it upward at 48 feet per second. The position function is negative 16t squared plus 48t plus 160. Now, by the way, the 160 is because that's the height of the tree, the height of the cliff. 48 is how fast the person threw it, and the negative 16 that comes from the force of gravity. Gravity is 32 feet per second, and in this formula you'll see this comes out to be, this is basically half. It's negative half the acceleration of gravity. Okay, so that's where the 16 comes from. Anyways, t is seconds, and we want to find the height and the velocity and the acceleration of the ball when t equals 3. So all I got to do is take the derivative twice. So the derivative of s is negative 32t plus 48, and that comes from just taking the derivative. Then the next derivative is just plain negative 32, and that's the that's the acceleration due to gravity. So gravity is a constant. Not yet. There's someone out. So there's someone. As soon as that person comes back, take the pass and go. So right, the pass is not there, right? Right. So this person's going to come back and take the pass and go. So so that's the story. So 32, that's gravity. Anyway, now that I have all this stuff here, I just got to plug in t equals 3 for all of them and get the position, velocity, and acceleration. Now the acceleration is going to be negative 32 because there's no t to plug in. So acceleration due to gravity is a constant acceleration. Okay, so for height, I just plug in 3 and it crunches out to 160 feet. Now wait a minute, it started 160 feet. So why is it after 3 seconds? Because it went up, and then it came down. It took 3 seconds to go up and down to where it started, and then it continues down after that. And then the velocity, just plug it in, is negative 48 feet per second. Just plug in 3. There's also certain symmetry there. Being at that point, it was going 48 up. Now at that same point, it's going 48 down. 48, velocity. And there you go. That is the story. So I love. I don't know why. There's one thing in physics I always like. Okay, how about gravity on the moon? Well, for on the moon, when you throw a rock upwards, the height, which is the position function, is going to be negative 27 tenths t to the second power plus 27t plus 6. So now the reason it's 27 over 10 is because the gravity on the moon is different than the gravity on the Earth. It's less. Anyway, I take the first derivative, I get negative 27 over 5t plus 27, same way I did before. I take the derivative a second time, I get negative 27 over 5. So negative 27 over 5, that's the gravity. That's basically the gravity on the moon, which is about 1/6 of what the gravity is on the Earth, in case you're wondering. And it looks like that's all they want. It's just the formula. They want anything else? No, that's it. I just wanted to get the formula for it. So that is the story. And if you don't believe me, just feel free to go to the moon and you'll find out. Alrighty. By the way, a lot of times we do things in metric. When you do these problems in metric, the 16 becomes a 4.9 because 16 feet is 4.9 meters. So, yeah. So I guess, yeah. So that's the story. And this is the last problem. Find the velocity of a certain automobile starting from rest. Oh, sorry. The velocity is v is equal to 80t over t plus 5. That's a velocity function. And we want to find this. We want to find the velocity and the acceleration at 10-second intervals, starting at 0 and going up to 60 seconds. Yeah, okay, the pass is back. Yeah. Okay, so the derivative, I have to use a quotient rule here. It's a quotient. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. This actually the ADT cancels out. So I am going to say here it pays to simplify because it just becomes 400 over t plus 5 squared. Now all we got to do is plug in t equals 0, t equals 10, t equals 20, so on and so forth. And here we go. Now, if you notice, the initial velocity is 0 because it's not going to, but that first oomph gives me is 16. It's very big acceleration. Because when you start driving a car, that first jolt is like, and then after 10 seconds, the acceleration is 1.78, then it becomes 0.64, 0.33, 0.20. You see the acceleration gets pretty much close down to 0. But the speed, the velocity actually increases as time goes on because it is accelerating still. So it's up to, after 10 seconds, you're going 53, and then 64, then 68, and 71. So, now it's if you notice here, in the first 10 seconds, it jumps 53. In the next 10 seconds, it jumps like 11. The next 10 seconds, it jumps like 4.5. And then it starts to jump very little because, the car starts to kind of like level off. The velocity starts to level off, which is true because when you first start a car, you feel that acceleration, and then once the car gets to a solid speed, you could be driving 100 miles an hour, but if you're sitting in the car, even if the car is going 100 miles an hour, you don't really feel any. You don't feel. The only time you really feel it is when the car is accelerating. You don't feel it when the car is just because of this. Like for example, you go on an airplane that's going 500 miles an hour, you don't feel any. You're just sitting there. You don't feel anything. But when it takes off, that's when you feel it. So that, my friend, is the. By the way, so change in position is velocity. Change in velocity is acceleration. Change in acceleration is called jerk. Because if you're accelerating, then all of a sudden you accelerate faster, you get this like feeling, you feel like it's a jerk. Like it's not, I'm not saying you feel like a jerk, but you feel this like jerk on you, like your body jerks a little. So that's change. That's just a physical. I'm just mentioning that's an interesting physics word, and that is that. Okay, so we're gonna give you we have some lovely homework, which I know you're gonna enjoy, because I know you guys live for homework, and we're gonna do all that, and it's gonna be fun. And let's see, we got some really cool problems here with velocity, acceleration, and this other kind of stuff. Well, that's it. We're done. Let's go back. I don't want that. Yeah. So this is the stuff we're gonna do. Anyway, I'm gonna post homework on Canvas like I always do, and we will see you guys next time. This has been 2.6 higher order derivatives, and that's it. I will see you guys on the next section. Bye everybody.